Yeah, I don't think I'm going to move from this place. So, wow. I can't talk to you privately anymore. Should we start? I just turned one.
I'll probably just hang out on the sides and answer questions.
Yes.
And just like walk around.
Yeah, I think that's what I'll do once I'm done.
Yeah.
And that I think is a smart thing.
Yeah. We usually have a lot of like people trying us individually.
Yeah, and we need to we need to run through the review.
Yeah.
Yeah.
So scary. There were like 2 drinks over there. Yeah, it's already recording. Did you set it up to record?
I think it's just automatic. I think someone scheduled it.
That's amazing. Yeah. Recording actually. Oh, that is very scary. Was that at 1.5?
Sure. Yeah. Hello. How's it going?
It's going. It's going. Midterm season.
Yeah. Yeah.
Oh yeah, I get to enjoy this week without midterms.
It's so nice. Yeah, it's you.
Hey, I have to spend years suffering, wondering when I'm going to leave. So I think that counts.
Okay.
Yeah. So everything goes in this bus, and then you must like the one way to like you create a constant function. That's what it's constant function. So you open the bus, you write the matter, and then you have something on them. It's really cannot be done in one time. Reading memory is actually that long. So that's just scroll which is that you're reading.
Part of it.
Like I feel like 21 we'll stop that. Nothing after.
All right. All right, everyone, let's get started. We are looking at the midterm review. We are mostly just going to cover topics in short. There'll be IAs walking around, so if you have questions, do stop them. We want to ensure we get through all the topics, so raise your hand and they'll come to you. So let's start out with some announcements. So just a reminder, the midterms on Wednesday from 6:30 to 8:30. Please arrive 10 minutes early. We would have already set things up before you get there. Only one side of a letter-sized paper, 8.5-inch by 11-inch paper is allowed. It needs to be handwritten. And ideally, so if you are taking the SSD or alternate exam, please ensure you know your room and assignments so that you can get there on time. Secondly, the room assignments have already been posted on Piazza, so ensure you know where you're seated and get to those places on time. When you get your exam sheets, ensure you've written the name first, because the moment time is done, we are going to be taking it from you, and it would be breaking of honor code if you're still writing after the time is done. So please ensure your names are written right at the beginning. There is no lab this week. There is no lab next week either because of spring break. And there's no lecture on Thursday as well. Any questions about these? Yes? We've not done lab 6 yet. Lab 5 is due 24th, which is tomorrow. And there's only a quiz section. There's no autograder section to that. Any other questions? All right, so let's start out. We're starting out talking about complexity and recurrence relations. There are 3 different ways to talk about complexity, which is big O, big omega, and big theta. So big O is essentially, you're talking about a worst case complexity, which is what's the max amount of time a particular code is gonna take, which is what is the worst case scenario. In case of big omega, like it says, it's a lower bound. So you're saying that it at least must take this much amount of time. And with big theta, it's a tight bound, which is you know that both the lower bound and upper bound are the same, and therefore you know that's the exact amount of time it's going to take. Just to intuitively understand what this would look like, you can think about this sort of arrow, which is you're moving from the slowest growing to the fastest growing. And the fastest growing is mostly where O of this thing tends to be, and that's the lower end of it. So, like it's written below, f of n is O of g of n when f of n is slower or similar growing than g of n. So, for example, if f of n is 3n, you can denote g of n as 2 raised to n or n factorial because it's faster growing than that. On the other way around, when you have omega of g of n, it sort of goes from right to left. So for example, if my f of n is n cubed, that can be denoted as omega of 1 or omega of n as well. Just one more intuitive thing. So when you're thinking about slowest growing to fastest growing, the things at the bottom are slowest growing because you can see that the time complexity doesn't really increase even though your input size is increasing. Whereas with n factorial or c raised to n, you're seeing that the time increases very rapidly right at the beginning. So just ensure that you understand how these things are related and you're moving from slowest growing to fastest growing. That'll give you an understanding of what O of a function is or what omega of a function is. Any questions about these? Actually, if you have questions, just please raise your hand and people will be walking around. All right, so we then talk about what average case complexity is and amortized complexity is. So average case complexity is just the average cost that a function is gonna incur. And you can almost think of it as if you have a random sampling of an input, what's the time that you're bound to take? So for example, if you've taken classes like 203 and 280, you would have encountered this scenario. For example, the std sort that you use from C++ has average case O of n log n time. With amortized complexity, it's average cost over multiple operations. We're not looking at a random case scenario. We are saying that if we know n operations are going to be done, and there's going to be a specific amount of work that's done at the beginning, what's the complexity over time? So an example that you've seen in lab 3 where we spoke about vectors, we can see that when you push back into a vector, that gives you amortized time complexity, constant time. So let's solve a small problem. So let's assume you have an ice cream shop where n customers arrive and they all buy a few ice creams. And which is why, so since you have few ice creams, it's going to be constant time because it's not changing based on the number of customers who are coming in. And let's assume at the end of the day, there is a food critic who shows up and says, how many ever ice creams you have sold over the day? I want that many ice cream raised to 3. I need to buy them right now. So given this state, what would be the amortized complexity of the total number of sales that are happening over here? So just to talk about, I'm going to just show you the average case, and I'm going to give you 2 minutes to think about the amortized case. So like I said, the average case complexity of selling ice cream is O of 1, since every customer buys only a few ice creams. But if you're thinking about the critique plus the number of customers who've come in, what would be the amortized time complexity? So take 2 minutes, think about it, and then we'll go over the solution. And talk to people next to you and discuss. You don't have to think about this on your own.
Yeah. Yeah, they're just watching cold stuff. All of chocolate. You know what driver does? Other consequent multiple of 1. Right. They are n minus 1. If you want coffee.
All right, so hopefully you've discussed some. Let's look at how that would look like. So the amortized complexity is O of n squared. So how do you get that? You know that you're going to have n customers, and they buy a constant amount of ice creams. So the total amount of ice creams that all the customers buy is going to be O of 1 multiplied by n. You then know that the critique is going to buy cubed amount of ice creams that customers have bought over the day. Therefore, you get O of 1 into n raised to 3. So this totally ends up giving you O of n cubed because we eliminate the smaller terms. So now we need to look at how many operations have happened, because we asked you what's the amortized complexity of selling ice cream. So then you divide it based on the number of sales that have occurred. Therefore, you end up getting O of n cubed by n plus 1. We are ignoring the constant term, and therefore you end up getting O of n squared. So whenever you're thinking about amortized complexity, always think about what's the total cost that has occurred and over how many operations it has occurred, and that's going to give you the amortized complexity. So just finishing up complexity, like we just saw, the lower order terms can be ignored. So if you have n squared plus n plus 1, you can just represent it as O of n squared. The highest order coefficient should also be ignored. You can see if you have 3n squared plus 7n plus 42, you eventually just refer to it as O of n squared. And the complexity of a loop can be inferred from bounds, but again, as an example that you've seen in one of your labs, sometimes the variable that's used can be decreasing, and that will change what the complexity of a loop is. So ensure that you're not just looking at your for loop line. Do check how the I value is changing. So that's the end of the complexity section. We're now going to be talking about Master's theorem and recurrence. And while we're changing, if you have any questions, just raise your hand. We'll come and help you out. Is that you? No, you can just use this. It's turned off. Oh, okay. Want to put it in your pocket, you can, but if you want to be standing. Okay, sounds good. Okay, can everyone hear me? Okay, so we'll talk a little bit about Master's theorem and recurrence next. So a recurrence relation is, it describes the overall runtime problem of size n in terms of running time on smaller inputs. So what that means is that a recurrence relation is a function that's defined in terms of itself. So in programming, we'll write this as a recursive function. So an example of this would be the Fibonacci sequence, and that was f of n equals f of n minus 2 plus f of n minus 1. So every time we run the Fibonacci sequence, we'll call 2 recursive calls on smaller inputs. So the way we find the runtime for a recursive relation is these 3 steps. So first, we'll identify the complexity of each recursive call. So every time we're running this, excluding the call to itself, how much complexity does this take? Then we'll take a look at how the input shrinks with each call. So are we calling like t of n minus 1? Are we dividing it and only taking a fraction of the input? Or how are we shrinking it? And then finally, we'll identify how many recursive calls are made every iteration of the function. So then our final complexity relation will be t of n equals part 3 times 2 and then plus 1. So we'll take a look at an example. So this is the factorial function. So taking a look at what we were mentioning earlier, we'll see what the complexity is of this function. So all we have here is an if statement. So if n equals 0, then we'll return 1. So this is an O of 1 case. So that gives us the last component in our recurrence relation. And the next part is our recursive call. So every time we call factorial again, we'll call it on n minus 1, which means that our input size is shrinking by 1 every time. So that gives us our t of n minus 1 relationship right there. And then finally, we're only calling this recursive call 1 time every iteration, which gives us the 1 in front of the t of n minus 1. So a lot of times when we have recurrence relations, we'll use the Master's theorem to calculate the complexity. So the Master's theorem is defined on the slide. Some things to note is that it has to be monotonically increasing. So this means that t of n does not decrease as n gets larger. And then we have to break up the input size of n into 1 or more subproblems that are a fraction of the size. So in other words, it has to be in the form of t of n over b, where b is greater than 1. And then finally, the additional work we do every operation has to be a polynomial function. So this is where f of n has to be some big theta of n to the c in order for us to use Master's theorem. So we have one example here. I'll give you guys like 1 minute to do this, and then we'll walk around if you guys have questions. But find the complexity of this recurrence relation using the Master's theorem.
Oh, that's right. The last thing is not a constant. We'll do ABS reading.
And it's a function of how much each happens, how much smaller your size of the size of the compound you see in the polynomial greatest degree of one
Okay, so our final recurrence for this, our final complexity for this recurrence relation would be O of n log n. And we get that by looking at A equals B to the C. So A is 2, B is 2, and C is 1. So then we take the middle complexity, which is big theta of n to the C log base 2 of n, and that gives us our final complexity of n log n. So this way of analyzing complexities is really helpful for a lot of functions that, or algorithms that we use within this class. So some examples are binary search, sequential search, tree traversal, etc. So these are just some examples of how you can use the recurrence relation and then find our final big O solution of what their complexity actually is. So just to reiterate, we cannot use Master's theorem if it's not monotonically increasing, if f of n is not a polynomial, and if b cannot be expressed as a constant. So an example of when not to use is if the input size is decreasing by 1. Any questions on Master's theorem? Okay. So if we can't use Master's theorem, then we solve recurrence relations using substitution. So the way we do this is through the substitution method. So we'll write out t of n minus 1, t of n minus 2, etc. And we'll substitute t of n minus 1 and t of n minus 2 into t of n. And then we'll repeat the process, and we'll look for a pattern, and then we'll use a summation formula to figure out the final complexity of this. So now we have another practice problem. So which of the following recurrence relations can solve one by applying, or can one solve by applying the Master's theorem? Okay, any takers for this question? Any ideas? Which of the recurrence relations we can solve using the Master's theorem? Yeah.
Would it be A and B?
A and B. Okay, so there's only one answer to this question. So between A and B, which one do you think would we be able to use Master's theorem on? Yeah. Yeah, exactly. So if we go back to our previous slide, we see that we can only use Master's theorem when A is greater than or equal to 1 and B is greater than or equal to 1. So in this case, in A is less than 1 because it's 1/2. So B would be our only answer. And then finally, which of the following pairs of complexity classes are not the same? So I'll give you guys a minute to do this too.
Is A not?
No, because it's too long.
Oh yeah.
I think they're all single answers. Oh yeah, There's like,
Oh wait, is this multiple answer choice? Single answer multiple choice?
Okay, so does anyone have any ideas for this question? Which of the following pairs of complexity classes are not the same? Any takers? Yeah. Yeah, D, right? So if we look at A, both of these are O of log n, and then for B, both of them would be O of n to the fourth. C, both of them are constant time, and then D, our first complexity will give us a big O of n, and our second one is just n log n. So those are not the same. Any questions on this? Yeah.
Can't you say that in B, the second complexity is O of n instead of O of n log n?
Oh, yeah. So you could say, actually, no, it would actually be big omega of n, right? Yeah.
The second part.
Mm-hmm.
Yeah.
Yeah, so n log n grows faster than n, right? So it would be a lower bound of n. But since we're doing big theta in this one, it would be the tight bound. So those would not be the same. Okay, awesome. Then we'll move on to arrays and linked lists. So in both of these containers, we can look at how they do sequential access and random access. So sequential access starts at the ends of the data structure, and they'll linearly move through to the nth item. So they can move in some iterative way. So examples for this are linked lists and binary search trees. So we can go from the first element to the second element and so on. And then we have random access. So this means we can directly access a point in O of 1 time. We can think about this in arrays and vectors because we can use the square brackets operation, and we can access any element within the array at constant time. So some things to think about for vectors are its capacity and its size. So capacity is the number of elements in the underlying array that it's capable of holding. So the way we adjust the capacity is using reserve. In the bucket analogy, this would be the size of our bucket. Size, on the other hand, is the number of elements added to the underlying array. So we can add elements to our vector using resize, and it will fill all of those buckets with something in it. And then pushback also increases our size. It achieves an amortized O of 1 because every time it reallocates, it will double in size. So if we do our amortization analysis that we did earlier in this review session, then we'll see that it achieves a constant amortized time complexity. So resize with the bucket analogy is filling the bucket with water inside, so it has elements inside. And then reserve is just changing the size of the bucket so that you can hold more elements. Linked lists, on the other hand, are sequential access only. So this is like a basic diagram of a doubly linked list. So there's memory overhead for the node data structure. In a singly linked list, each node contains a pointer to the next node. But in the picture, we can see that a doubly linked list has our next node and the previous node. And then our variants are that the last node has to have a next pointer of null pointer. And then if the list is empty, the root node will be null pointer. So when do we use each type of container? So in general, vector is the most efficient. So it's cache friendly, which you guys don't really have to know much about, but basically we can access the data more quickly. It's amortized O of 1 push, as we mentioned earlier. And then if your data types are small enough, then copying and moving will not take up a lot of time. But when we want to use a linked list is if our code is dominated by splitting and merging off very large lists. So if we want to be able to quickly and effectively move like large portions of the data set, it might be easier just to switch around the pointers rather than copying each element over. If there's lots of inserting or deleting from the middle of the list, we would also want to use a linked list because of the pointer structure. We don't want to have to shift all the elements every single time we insert or delete from the middle of the list. And then finally, if we have measured and profiled that it's more efficient, then we would want to use the linked list version. So this is a chart showing the main differences between the arrays and linked lists. So just to highlight some important things, random access in arrays are constant time, as we mentioned, because of the square brackets operator, and it can do pointer addition. Linked lists, on the other hand, are random in O of n time, because if you want to access an element in the middle of the list, you would have to traverse through each element's next pointer until you reach that element. And then for memory, arrays have an advantage in that it doesn't have to have the overhead of the pointers if you have like primitive type elements, but it does waste memory if it's oversized. So if we think about our vector, if it reallocates and doubles in size, then there would be a lot of memory wasted. And linked lists, on the other hand, they'll only allocate memory as needed. So every time you create a new node, it will just allocate space for that one node. But again, it requires the memory for the pointers. So those are the trade-offs. And depending on how you want to implement something, you can decide which one is more efficient for your needs. Okay. And then assume you're given a pointer to the node you want to delete. Can we delete it in O of 1 time? So if we have a doubly linked list, then it's trivial. We can just switch the pointers, switch like the next pointer to the pointer after the node we're deleting, and then the next node after the node that we're deleting will switch the previous to its previous. But what about a singly linked list? I'll give you guys like a minute to discuss.
It's having to Amortized Complexity.
Bending to a
Yeah, I don't see this one.
I can see.
Because you need to increase the size.
I think a bending may not be.
Bending,
So I said over for one time or is it over for average?
it doesn't say anything, you just say all one.
I think it's.
It should be amortized.
Yeah, I don't know if it should be amortized because we are spending it means that the size is.
We should not be quantitative.
Not right about its own fun. I don't think it's amortized. I think it is just more fun.
Why is it not amortized?
Because so the reason inside is amortized is because you are expecting your to push back. With append, you are never doing pushback. I think with pushback, you're thinking of circle back. With append, you're saying, I have this capacity, and I'm going to append the value to like you put it. So it's not so but you can append in over fun time of the for linked list, you can't get over fun time unless it's
Okay, so if we want to find the complexity of deleting a node from a singly linked list, all we have to do is we can overwrite the data in our node to delete with the next node's data, and then we'll delete the next node. So this assumes that data can be copied or moved, but this allows us to delete the node. Okay, so now we'll try this problem. So what are the contents of the output vector after this code runs? Give you guys a few minutes to try this out, and we'll walk around if you guys have questions.
Actually, this is not practical.
right.
No, I used the other side. So I think it's 6 is 1, 7 is plus 2, 5 is plus 3, 3 is plus 4.
Wait, let me press the
Can you not see this?
I cannot see this, which is why I give you the black. Also, before you do this, can you talk about the fact that singly linked list was constant time? I don't think that was obvious to.
Oh, the previous slide?
Yeah. Just.
If it takes BPN, how much is it? That is usually the one that.
Okay, so we're going to bring it back to the previous slide. So this wasn't clear earlier, but when we're deleting a node in a singly linked list, we can actually do this in constant time. So when we overwrite the data with the node to delete with the next node, and then we delete the next node, we can do that all in constant time. So back to this problem. The way we can look at this is we start with the second line. So we have our output vector, which goes from input.begin plus 1. So we can think of this as an iterator that points to 6. And then input.begin plus 4. So this would point to 3. So if we remember, usually when we have a range, we'll define it as inclusive to begin and exclusive to the end. So that means our output vector will only include 6, 7, and 5. So then we have our output vector of 6, 7, 5. In our next line, we're going to resize our output vector and filling the new spaces with 1s. So we'll resize it to 6, so we'll add 3 1s. And then finally, we want to resize it to 8. And when we don't pass in a value, we'll just fill it with default values, which in this case would be 0. And this gives us our final vector of 6, 7, 5, the 3 1s, and then the last 2 zeros. Any questions on this one? Okay. Then we'll move on to our next question. So given a linked list with n nodes, which of the following statements is false?
I'm so sorry.
Okay, so let's walk through this problem together. So how many people think A is true? How many people think it's false? Okay, yeah, so if we have a singly linked list, we can reverse it in O of n time. So we can use this, do this using about 3 pointers. And all we have to do is keep track of the first element and the second element, change the second element's next pointer to the first element, and then continue on. How about B? Anyone think B is true? Okay, how about false? Yeah, so finding an element in a linked list takes O of n time because we have to traverse through the elements to get to that. And then for C, the last element in a singly linked list with a tail pointer can be removed in O of 1 time. So true. And how about false? Okay, yeah. So this one would be false because even if it has a tail pointer, it would not be able to be removed in O of 1 time. Actually, I think this contradicts our previous slide, doesn't it? C.
You don't have to move the tail pointer up there, which is why, like the point is, why would you even need a tail pointer is another thing. So the tail pointer will be there to add a value, but if you're deleting the value, the tail pointer needs to move backwards, and you don't have a pointer you can going backwards. That's why it's hard to do.
I think the tail pointer is like a
Yeah, unless you're adding elements. So if you're appending elements, tail pointer gives you O of 1 adding time, because otherwise linked list adding a node is O of n time. So tail pointer lets you add it in constant time, right?
Yeah, but we're talking about.
Yeah, exactly. Removing is not constant time. Removing will be O of n time.
But in our previous, so this one.
But that's because here there's no tail pointer, so it doesn't matter. Here we are just saying copy the node and change it. Here we specifically need to edit the tail pointer as well. That's the problem.
In this one, we're given a pointer to the thing we want to delete. So in this thing, we
Are you there?
I see what you're saying. Can't really do it.
I think it makes sense. It's false. I will take you have the next value. So since you have the next value, you can just calculate it out and then you can delete the next one because you have the next pointer. So the only I think the only problem with this one is the tail pointer because the tail pointer makes it harder. Here, since you have a pointer to the node, you get constant time. In case of tail pointer, even though you have the constant node, there is no next pointer, so you can't just copy data in, which you could do over here. You want me to explain this just because?
I think this slide's actually wrong. I think the one you're pointing at right here, I think this slide is wrong because it always happens.
Yeah, but even then, if there's no always a next node, then that just becomes null. It doesn't matter.
But you can't copy the data. There's no data.
Oh, yeah.
So I think this slide is wrong in the case of this one.
Yes.
But yeah, I would say go with the other slide.
Okay, sorry about that. So just to clarify, this slide assumes that we have our next node to copy our data into it. But for the edge case where we are deleting from the tail, then this would not be applied. So in this case, if we want to remove the last element in a singly linked list, then the tail pointer would have to take O of n time because we would have to readjust the tail pointer and we would have to traverse all the way through to do that. If you need any more clarifications, we can walk around and answer your questions. Okay, so we know that C is false, but just to look over D and E as well. So bubble sort, insertion sort, and selection sort can all be implemented for a singly linked list using O of n squared time. So this is true because it's just the same as an array-based container, except we're just switching up the pointers rather than swapping the values. And then E, arrays waste space when not full, when linked lists waste spaces for storing pointers. So if we go back to our chart that we had earlier, this is true because the downside for arrays is that we can have extra space that we're not using, and in linked lists, we'll waste space for storing pointers. Okay, so I think this will be our last question for this section. So we're given a function with 3 parameters passed by value. So we have our head pointer to the first node of the linked list. We have our tail pointer to the last node of the linked list. And then we have an integer k. So we want to assume that the data stored in the linked list cannot be copied, and the integer k is always greater than 1 and less than the size of the linked list. So looking at 1 through 4, which of these can we implement without creating any new local variables?
We don't know some, but not necessarily. If you have the one before each, like that is equal to
None of the above you argue that variables are. No, we don't.
Okay, so let's walk through this problem. So how many people think the first functionality can be implemented without any local variables? No one? Okay. How about the second one? So deleting the kth node of a doubly linked list. Can we implement that without any extra local variables? Okay, and then how about 3? So we switch the kth node with the k+1 node of a singly linked list. Maybe? Okay. And then how about the fourth one? So we switch the kth node and the k+i1th node of the doubly linked list. Okay, so we got a lot of takers for 2 and 4, but we actually find that we can do all of these functionalities because these 3 parameters are passed by value. So it's kind of tricky. So because it's passed by value, we can safely move the head and the tail, and we can keep track of whatever we want when we're deleting it. So. Okay. Okay, so then I'll pass it on, and we'll talk about some more container types.
Just a clip? Perfect. Can I say one thing? Yeah, please. Hey guys, real quick, I just wanted to announce we posted the review slides. It's on the midterm exam review pinned post on Piazza. It's 2265. I'll write it on the board. If you guys want to take a look at those or just follow along as we go further.
All right, can you hear me? All right, yeah? Question? Oh.
Okay, so you guys hear me? Okay, so we'll go back to the last question. So we can walk through each of these really quick. So if we want to delete the kth node of a singly linked list, all we have to do is we just move the head pointer to the kth node. So we just say like head equals head next for k times, and then we'll be able to delete it. And then if we want to delete the kth node of a doubly linked list, it's the same thing. So, sorry, do you have something in there? Okay. And then if we want to switch the kth node and the k+1th node of a singly linked list, we can do that because we can also move the tail pointer wherever we want. And because we know that k is a valid integer, like the kth node, we don't have to do any checks that we like go out of bounds. So we can use the head to keep track of the kth node, and then we can increment, we can set like the tail equal to where the head was, and then also increment that k+1 times, and then we can just swap the respective pointers. Okay. Any other questions on this one? Yeah.
So is there anything that singly linked list can do but doubly linked list? Or sorry, the other way. That doubly linked list can do but not singly linked list?
Yeah, so in this case, there is no difference because we have all of the parameters passed by value. But in the case where we want to be able to set like the next pointer for a singly linked list, or if we want to delete a node, then we would need to have 2 pointers consecutively so that when we delete a node, we can set the previous's next to that node. Yeah. Okay, are we good on this question? Okay, and we'll move on to our other container types.
All right, can you hear me all right? Yeah? What? Oh, yeah. All right, cool. So we're going to talk about container types now. So let's go briefly. What is a container? Container is a class, data structure, or abstract data type whose instances are collections of other objects. In other words, they store objects in an organized way that follows specific access rules. We're going to go a little bit more into what that all means. Cool. So here are different types of containers. One thing to note is that they are not mutually exclusive. You can just go over them real quick. So a container supports add and remove operations, as you can add things to this container and also remove stuff. A searchable container means that you can find, right? So you can find things within this container, see if whether or not they exist. A sequential container allows iteration over elements in some order. A ordered container is a sequential container which maintains current order, which means you can arbitrarily insert new elements anywhere. For example, books on a bookshelf. You can insert a new book anywhere within that bookshelf, right? And all of the rest of the books will relatively stay in the same order. Lastly, a sorted container is a sequential container with predefined order. It means that you cannot arbitrarily insert elements. So, for example, students sorted by ID. You cannot insert a new student with a unique ID just anywhere you want, right? Because that container is sorted. So here are interfaces for sorted and ordered containers. Essentially means how you can interact with them, right? So sorted containers allow you to add elements, remove elements, find elements, operator, essentially being able to randomly iterate. You have withdraw. One thing to note is that ordered containers allow for insert after or insert before, whereas sorted does not, because a sorted container, those elements still have to be in that sorted order, so you cannot arbitrarily insert just like before here or insert after here. All right, cool. Here are some common container complexities that you should know. We divide this out in between ordered and sorted containers, right? So for an ordered container, if that container is an array, here are the time complexities for all of these operations, right? So we have the square bracket operators, O of 1 for an array. It's O of n for a linked list, right? Because you have to iterate through the entire linked list, or iterate through the linked list in general. Insert after is O of n for an array, because in order to insert into an array, you probably have to move a bunch of elements off or over by one. Delete is O of n for the same reason. If you remove an element from the middle of the array, you do have to shift a bunch of elements around. Whereas linked lists, insert after and delete are faster. They're O of 1. For sorted containers, we have something interesting here that we can do array find in log n time. Can anyone tell me why that is, potentially? Yeah. Binary search, correct. So we can do binary search on a sorted array, and then we're able to determine whether or not that element exists in our sorted array in log n time. We cannot do this in a linked list. So linked list still takes O of n time, even for a sorted linked list. A square bracket operator, an array is O of 1. Linked list is still O of n. Delete O of n for an array, and linked list O of 1. Cool. All right. So here are a bit more complex definitions for sorted and ordered containers. A sorted container is specifically an iterable/searchable container that maintains a strict value-based comparison ordering that determines the order in which elements are iterated over. Right? So if two sorted containers contain the same exact elements, they are identical given that those two sorted containers are sorted the same way. Whereas for an ordered container, it is a general container where each element deterministically maintains its position specified by the user regardless of what elements are added after it or came before it. For the example of the bookshelf, right? So you can insert a book anywhere within that bookshelf, and it shouldn't change the relative ordering of any other book in that bookshelf. For every collection of n elements, there may be n factorial different ordered containers that hold them. Basically, what we're saying here is that for n elements, there are n factorial different ways that you can order those elements, right? So you can have n factorial different ordered containers for those n elements. Cool, so some clarifying questions. Is a priority queue iterable / searchable? I'll give you guys some time to think about that. And the second question is a priority queue an ordered container? We'll give around like a minute or two for you guys to think about that, and we'll get a show of hands.
There's no interface for it. You can do PQ.data. There's no
PQ.data,
that's a vector.
That's a vector, yeah.
Technically, it doesn't have an iterator.
But you don't have an iterator.
A queue doesn't have an iterator. Only a vector has an
Queue is not because if I push something in, it could not.
Yeah. It's a sort of
All right. First question. Is a priority queue iterable / searchable? I can never say that word, iterable. Raise your hand if you think it is. Okay. Raise your hand if you think it's not. Nice. Raise your hand if you're unsure. Got it. Cool. And we'll keep that in mind. Second question, is a priority queue an ordered container? Raise your hand if you think it is. Okay, got a few. Raise your hand if you think it's not. All right. Raise your hand if you're unsure. There you go. The answer to both these questions is no. So a priority queue is not iterable / searchable, right? Because when you basically when you have a priority queue, you're unable to look into it, right? You only know what element is on top and what elements go in. Is a priority queue an ordered container? Also no, because you only care about the priority queue's priority, right? You care about what is the maximum priority, right? So it has no relative ordering to it. Cool. All right. So, follow-up question. Take a look at these statements and discuss amongst yourselves what statement is false about sorted and ordered containers. A, add element can be implemented in O of 1 operation in an ordered container, and an O of n operation in a sorted container. B, both sorted and ordered containers can support insert after and insert before. Both sorted ordered containers can be implemented by either a linked list or an array. D, both sorted and ordered containers inherit some of their implementation from searchable containers. Or E, all of the above is true. All right, discuss amongst yourselves. That's not me. That's not me.
Oh, is it?
Yeah.
Oh, is this the new section?
Yeah, I think so.
Oh, gotcha.
Maybe. Right.
I was like, I thought this was the same section, but I might be wrong.
I can do it. I mean, I don't mind. Can you double check that?
Let's check.
Yeah, I think it's still you.
Okay, cool.
Yeah.
Yeah. Which one are you
So I
gonna
was thinking skip this one and then the more practice questions.
Sure.
Just 'cause
It's long, yeah.
yeah, it's going to take a while to do those. So
Yep.
if we could do this one and this one, and then the one right after this.
Yeah. I think that's
This is the one from lab, I think. So it's probably good to go over that.
Yeah. I mean, you should have gone over in lab, right?
Yeah.
Cool. Okay. Yeah.
Is that good?
Yeah. Absolutely. Actually, can you show me which one that was again?
Which ones?
The one you want me to skip.
This one and then the more practice.
Which one is
just
well?
this.
Okay. Cool. All right. Cool. Raise your hand if you think the answer is A. Raise your hand if you think the answer is B. Okay, wow. Raise your hand if you think the answer is C. Do we have a D? What about an E? All right, cool. So the answer is, in fact, B. As evidenced by the actual, I think, like 2 slides before, both sorted and ordered containers cannot support insert after and insert before operations. Which version can? Ordered. Say ordered. Someone say ordered? Yeah, okay. So ordered containers can. Cool. We're going to hop into this question, which I think we did cover a little bit in lab, so I'm going to give you 30 seconds maybe. Just go over it. Think about it.
So what kind of containers are those?
All right, that's about 30 seconds. Cool. Raise your hand if you think that, and these are for statements that are true. You're trying to answer which one is true. Raise your hand if you think the answer is A. Raise your hand if you think the answer is B, C, D, okay, E. Cool. So the answer is, in fact, D. Binary heap's underlying data vector is neither ordered or sorted, right? So if you insert something into a binary heap, it can change the relative ordering of things in general, and the container underneath, right, it's a vector, and that vector is definitely not sorted, right? Even though a binary heap may be on the top priority, may be in some order. Cool. We're going to hop into stacks and queues. Cool. Here is a quick overview of how you can implement a stack and a queue in STL, decks, which y'all should be familiar with your projects, and et cetera. You can optionally use a list or a vector for a stack. Queue, you can optionally use a list, right? And the reason being is, let's go over stack, for example. Stack is a last in, first out container. What that means is that you have, for example, a stack of papers, and you can put things onto the top of the stack of papers, and you can only remove from the top of the stack of papers, right? So that's an easy way to think about a stack, right? You can push values on top of it, you can pop from the top, check what's on the top, you have the size, and you have whether or not the stack is empty. Whereas for a queue, right, think of a line where you get into the back of the line and you can only exit from the front. So you push values to the back of the queue, remove values from the front, check what's at the front of the queue, you have the size, and you have whether or not it is empty. So another question. Which of the following is most accurate about stacks? And you can just read over them. I'll give you another minute or two to discuss amongst yourselves.
I know, right?
All right. Raise your hand if you think the answer is A, B, C, D, E. Okay, so the majority of you said D, and D is correct. Stacks can be implemented using an array or a linked list. And then we are going to, are we skipping this one? Yeah, cool. There's the answer for it if you want to look over it for 5 seconds. But we're going to hop into a different question. So D is correct for the last question. Suppose you're given an STL container, either a stack or a queue, containing n integers. You need to determine whether it has any duplicate elements in it, but you are only allowed to use O of 1 additional integer variables. The container that you are given can be reordered or even emptied during your check. Which of the following is the most accurate about the feasibility and worst case time complexity of algorithms to solve this problem? Clarification, you could have 2 different algorithms, one for a stack and the other for a queue. Cool, this might take a little bit, so we're going to give you more time as well. Think about it. All right. We're going to hop over to what you guys think the answers are. So raise your hand if you think it's A. All right, raise your hand if you think it's B. Raise your hand if you think it's C, D, E. Raise your hand if you're unsure. Got it. So the answer is, in fact, B. It is impossible for stacks, and worst case, O of n squared time for queues. Does anyone have a suggestion for why this is? For people who said B. Yeah.
For the stack, you can only, you need to pull everything out of it. You have to have O of n additional integers. So with the queue, you can always loop through the whole thing by copying off the front, putting it back with one variable. So you only use 2 to compare, or actually just one, and you can compare everything. Versus stacks, you have to go through the whole thing.
Gotcha. Great answer. So basically for stacks, you would have to essentially empty the whole thing out, right? And you're unable to check what's at the bottom of the stack without emptying the whole thing. Whereas for queues, you can essentially take what's in the front, check it, and put it back into the queue, right? And you're able to loop through the entire queue that way. Which is why you can do it for queues. It's impossible for stacks. But for queues, it would take O of n squared time, right? You would have to check every single element in that queue. Cool. We're skipping this, right? Cool. Yep. And then let's just finish off with decks, right? A deck can be used to support efficient back and front access. It's essentially a stack and a queue all in one. You can use to traverse it using iterators and also the square bracket operator. You can use that. It supports O of 1, push front, push back, pop front, pop back, front back, and operator, square bracket operator. So it's really, really useful. For example, you can use a doubly linked list, but what's the problem with the implementation if we use a doubly linked list for a deck? Yeah, exactly. So for a doubly linked list operation, implementation for a deck, the square bracket operator will be O of n, right? So that is no good. Cool. And we're going to hop over to set union and find. Set union find. That's set, yeah.
Yeah.
Oh, yeah.
All right. Can you guys hear me? Okay. So yeah, we're going to go over sets and union find now. Our favorite topic. Okay. So a set, just to start off with some definitions, is just a searchable collection of unique elements where elements can be compared for equality. So some operations we might want to do on sets are union, which is take elements of A or B. Intersection, which is take elements of A and B. Difference, which is take elements of A that are not part of B. And symmetric difference, which is XOR equivalent of all of those. You can see the operations over here. So we have intersection, union, difference, and symmetric difference, which is also the complement of intersection. Any questions on these operations? And then we're going to go into like when you would want to use a set. Okay. So in each of these situations, your task is to decide would it make sense to use a set or not. I'll give you a minute or two to think about this, and then we'll come together and bounce some questions off of each other. You can discuss.
Was
And really what we're talking about for these is can you do this efficiently, not whether you could do it in theory.
We could make everything on a set. Universal set. It's possible like check for membership.
Okay, so let's start going through these. So for the first one, raise your hand if you think this would be a great use for a set. Raise your hand if you think it wouldn't. Okay, so I would agree. I don't think this is a great use for a set. Basically, sets aren't very helpful when you need to know what's not in a set. They're only helpful for knowing whether something is in a set. And especially in this case, if we're trying to find the smallest positive integer not in a set, the only real way to do this is to iterate over all integers starting at 0 or negative whatever and try and find them in the set. So in this case, that would not really work out. What about the second one here? Any yeses? Any no's? I would again agree with the no's. So in a restaurant, you might have duplicate orders pretty frequently. So I don't think it would make sense to keep these in a set because then you would lose duplicates and you would have angry customers. What about number 3 here? So we're keeping track of what items are in and out of stock in a store. Maybe you'd use 2 sets for this. How's that? So who thinks this might be a good idea? And who thinks it would not be a good idea? Yeah, so I think you could use a set in this case. So 2 disjoint sets, one for what's in stock and one for what's out of stock. And you can quickly query what's in stock and what's out of stock when you're making an order. So what about number 4 here? We're trying to obtain a list of students who are both seniors and in computer science. Who thinks yes? Who thinks no? I would agree again. So yes, so if we have a set of all people who are seniors and we have a set of all people who are computer science, we can intersect them together to get all people who are both in computer science and seniors. So again, just going over the answers in written form here. There they are. So that's kind of like sets at a high level, but we can also implement these using different containers under the hood. So sets can be represented using any searchable or iteratable container. For sorted data, all set operations are in linear time. For unsortable data, set operations generally take n² time with exceptions. And we'll get to hashing very soon to cover that. But this is kind of at a high level how you might implement these and what the complexities might look like. Are there any questions on sets before we get into disjoint sets? Okay. So disjoint sets are sets that share no elements. Generally, if we have disjoint sets, we may want to union many of them together. And our previous methods aren't great because we have linear time per union. And that's worse than we'd like. And in the unsortable case, we have n² per union. So we don't really want to do that. So generally, in this case, we're doing a lot of unions. So the complexity is going to matter. So union find is how we can do this. Union combines 2 groups together. Find returns the chief of one group. And then we're going to typically represent this using an array of integers, which map IDs to other IDs in a graph-like structure. So each knows who represents them. And then using representatives, we know disjoint sets based on whether 2 representatives are the same. So going into this, we have a broken implementation shown here. So I'll give you a quick second to look at what this is doing. Rep is our array of mapping from ID, which is the index, to ID, which is the representative for that index. So if we union by just setting the representative of one to be the other, we'll see that this breaks. Find in this case is fine, but it might not have the complexity we want. So we'll get into that in a sec. But to show why union is broken in that case, let's say we wanted to union 3 and 4 together. Using our previous implementation, we would take and set 3's representative to be equal to 4. But you'll note in the previous slide that 0 and 1 used to be in the same set as 3. And now they're not. So we've just broken a set. And we don't want to do that when we're unioning. We want sets to stay together. But we want disjoint sets to union together. So we don't want to union 2 but create another disjoint set. So this is our fixed basic implementation. So this is like the simplest version of union find you can do. You'll note instead of doing the union by setting the representative of A to be B, we instead find the ultimate representative for A, find the ultimate for B, and then set their representatives equal. And we'll see in the next slide that this fixes the issue. So now if we take 3, we find its ultimate representative, which is 1. And we find 4's ultimate representative, which is 6. And we set 3's ultimate representative to be the ultimate representative of 6. There's a lot of words there, but hopefully it makes sense in the picture here. Does anyone not understand what I just said? Okay. Does anyone have any questions on why the previous implementation was broken and why this one works? Yes?
Just to confirm, we need to find the ultimate representative of B because
So actually, so in that case, you could have done without finding B's ultimate representative. It wouldn't break anything. But in this case, because we're modifying A's representative, we do actually have to find there. It'd just be less efficient if we didn't find B, because eventually it would make our path longer. Does that make sense? So it would be correct to rep find A equals B. But for symmetry, we do it on both. Any other questions? And we can actually, if you can prove that to yourself if you look at this example again. If we set 3's ultimate representative to be 4, you'll note that they're still in the same set with 6. They still have ultimate representative 6, so it still works out. It's just less efficient when we do subsequent finds. Yeah?
So we're not doing path compression?
Not yet. We'll get to that in a sec. This is just vanilla union find inefficient. Okay. If you have any questions, interrupt me. So our first path compression is actually path halving. So this isn't full path compression. This, when we call find, this is going to take the length of every path and cut it in half. So we take every representative and we point it to one that's 2 away from it. This code doesn't make sense reading it as much, but I think it makes more sense if we look at it. So if we call find on 5, it's going to return 1 in the vanilla case. We're also going to modify 3 and 0's representatives when we do this. So you'll note that 3 skips 0 and points directly to 1 now, and 5 skips 3 and points directly to 0 now. So we halved the length of the path in each case, right? 5's path length was 3 before, and now it's 1, and 3's path length was 2, and now it's 1. Does that make, yes?
It's only halved in this case already.
It's halved in every case, in the general case. Roughly half. Not exactly half, but yeah, half up or down by 1, yep. Okay. So this is full path compression. So in this example, we set every representative we see along the way to the ultimate representative here on this line by making this recursive call. So in the top case, if a representative is represented by itself, we know it's the ultimate representative, so we can return out. This is our base case. In the second case, we are setting the representative equal to the ultimate representative, which we find recursively. Otherwise, we are returning the ultimate representative, which we just set in this recursive case here. So this is full path compression, which means all of the things along the path from 5 to 1 are going to be set directly to point to 1 after this. So paths end up being as short as possible after this call. They don't necessarily stay this way. So when we, for example, union 0 and 4, you'll see 0 up there and 4 down here. When we union them together, we end up pointing 1 to 6 and 0 to 6. But 5 and 3 no longer have the shortest paths possible. But this is OK, because in the general case, we'll call find on one of those again and end up shortening them later. But it's too expensive to iterate through all things which point to everything on the path and set their ultimate representative again when we do a union. So there's a reason we don't do it here. Any questions on this path compression? Yes?
Would there ever be a reason to do path halving instead of full path compression?
They have the same complexity, but in the second case here, we do full non-tail recursion. So if you're limited in stack space, you may want to do path halving because it doesn't require as much stack space and it still gets the same complexity in the end. But in this case, you get better path lengths, so it might be faster. You'll have to play, like, this is kind of an implementation decision at that point. Yep. Any other questions? Okay. If there are no other questions on union find or sets or disjoint sets, then we will move into STL and iterators. And I'll be walking around to answer more questions. Oh, sure.
Can everyone hear me now? Cool. How's everyone doing? That's good. So I'm going to just give a really quick overview of the STL, what the functionalities we've covered in lecture are. So these are pretty much all of the different data structures that we've used in this course. You've seen them in either lecture, discussion, or you've used them in a project. But I would recommend knowing the different functions that are available for each of these. You should know the complexities of those functions, and then you should also know when you would like to use either of these. So there are a few more data structures that we're going to be covering eventually, but for now, for this exam, you should know all of these from front to end. So for a few of these, like the vector, deck, and list, we know that the vector is very compact in memory. So that just means that we can, all of the elements in the vector are adjacent to each other in memory, so we can use random access to access those quickly. Something to keep in mind is that if you want to use a random insert or erase, that would usually require linear copying because you have to move over elements to make room for the new elements. And you may also have to resize your container as well if the size is ever equal to capacity. For the deck too, similar to the vector, you can use random access for it. The thing with the deck though is that it supports both the pushback and front as well as the pop back and front operation. How many of you guys used a deck in Project 1 or Project 2? Yeah, so you guys have used this before, and you should know when using that is useful. The list, on the other hand, is basically a doubly linked list. When you create a node in a linked list, it could be anywhere in memory. If you have a list of different nodes, then all of those nodes are usually at completely different memory locations. So you're not able to use random access for those. But let me see, random. But since it's a doubly linked list, you can insert and erase an element in constant time with a list. So we have an example here of a priority queue. We want you guys to figure out what must be true about orange, the type that we're passing into here. Disregard choice E. Yeah, it is true, but that's not the point that we're trying to get here. I'll give you guys like maybe 2 to 3 minutes to kind of talk about this problem with your neighbors, and let's see if we can come up with an answer to this. Maybe like 30 more seconds. Okay, let's bring it back. Does someone know the answer to this problem? At the very back. Yeah, exactly. With this syntax here, by default, since you didn't pass in a comparator, the default comparator that the priority queue will use is the less than comparator. So you may have seen examples where you would have like a priority queue of integers or like a priority queue of doubles. With primitives, those primitives can support a less than comparison. But if you have some custom type called orange, you would have to make sure that that type can support the less than comparator. And if you want to have an ordering that's different from like less than, then you would have to specify the comparator that you want to use in that declaration call. What questions do we have regarding this example? Yeah.
Does the parenthesis mean the copy constructor?
That's the call operator.
Oh, the call. Okay.
Yeah. Any other questions before we move on? Yeah. I'm sorry. Why is it not B? That's just because the default comparator, with the way it's implemented in the STL, it can only support the less than operator by default. That's just mainly like an implementation detail. Did this make sense to everyone? Okay, for the sake of time, I'll move on. So, in addition to the data structures that we've went over, there's also a few algorithms that are really useful to know. For each of these algorithms, they require you to pass in iterators to the range of the data that you want to do the operation on. So there's essentially two different types for these. There's a random iterator, which will support you starting at any location in the container and going up to the end. Whereas with the forward iterator, that can only ever start at the beginning and go to the very end. So with the random iterator, you can start at like any point in the container and then go to the end. With the forward iterator, you can only start at the very beginning and go to the end. And these are also the complexities for each of these functions here. So you can kind of think of iterators as pointers, but if you have an iterator to a container, what you can do is you can dereference a given value that you're pointing at with the star reference, and you can increment that iterator to point to the next adjacent element. So this is pretty much the interface that is going to be used for using those data structures. So like in this example here, to sort this vector of doubles, we would pass in the beginning iterator for the vector as well as the end iterator. If we want to, say, remove 1 from this range, then we would just use the list begin iterator and its end iterator. Does this make sense to everyone so far? Yeah. I would recommend knowing that just in case you might have a question where you can use the STL and you should know like what type of iterator it needs. Yeah. So each of these iterators are supported by the vector string, list, and deck containers. So you'll have a .begin iterator, which is inclusive. That just means that the iterator that this returns is going to be the first element. It's going to include that element. The end iterator is always one past the last element. So we say that is exclusive. that just means that it's going to point past the last valid element that's in the container. Then you also have constant iterators, which don't allow for you to modify the values that you're referencing. And then there's also two types of iterators called RBegin and REnd that work backwards. So the way these work is that if you declare it, instead of pointing to the beginning, it's going to point to the last element that's in the container. And then if you increment that, it's going to actually go backwards. So with REnd, that range is going to be 1 before the first element. And since the iterator type names are really long, I would recommend just using the auto keyword to declare them. Oh, yeah.
Can you compare a begin iterator to an RBegin iterator using the equals operator?
I believe you can do that. That should be fine. Yeah. Yeah.
So, would RBegin return the null pointer in front of the first element?
RBegin.
Wait, no. REnd.
Oh, REnd? Yeah, REnd is essentially a null pointer.
Just the thing right before we start.
Yeah. So here's another example. I'll give you guys 2 more minutes to figure this one out. But you have a string here, and you want to figure out what is going to be printed as a result of using the range-based constructor to create the string. So I'll give you guys maybe like around 2 minutes to go over this one with your neighbors and figure out the answer.
Oh, I think RBegin separates.
Wait, so would it include a dash?
No, because the -7 is x. 1, 2, 3, 4, 5, 6, 7. The dash.
Wait, so is x not about the iterator, but about the string part?
Well, next one is I go up to not on that.
What doesn't the minus actually works on regular iterators? It's like vector like I think
Vector must have
Okay, let's bring it back. Would someone like to give the answer to this problem? You guys can shout it out if you want. Yeah, that's it. So what happens here is that RBegin is going to start at the last element that's in the string. So that's that S. And normally REnd would be 1 past the first element in the string. But since we're subtracting by 7, our offset is going to move to around here, I believe. So when we create this string using these iterators, it's going to create it from right to left. So that ends up creating a string called stress no sleep, and it'll print that out. Before we move on, are there any questions regarding this example? Yeah. Yeah, that's right, Nini. It's reversed. So when you increment, you go from right to left instead of left to right. Yep. Cool. And if you have any follow-up questions, feel free to raise your hand and someone will come around and answer you. So there's different kinds of iterators, and each of them have different capabilities. Technically, they're not types. They're just like basically a keyword that specifies if you create an iterator of any of these, what are their requirements? So the input iterator and output iterator can only read and write values while moving forward. The forward iterator can both read and write values while it's incremented, and the bidirectional and random iterators have a little bit more power than those previous three. With the bidirectional iterator, you can still only strictly go left or right, but now you can move in either direction and you can read and write a value. The random iterator is the most powerful of these, and you can basically start at any given point in that container, and then you can do essentially pointer-like arithmetic and comparisons with that type of iterator. Do you guys know of a operation supported by pointers that is not supported by iterators? Yeah, Dan? Yeah, exactly. Yeah. With an iterator, you can't use the delete keyword on it. Before I head off, do we have any last minute questions regarding the STL and what you should know? Yeah. Oh, an example of this. So I believe these are like iterators that could be in the list class. So you would make an input iterator to that list, and then you would only be able to like start at the very beginning of it, and then you could increment it until you get to the end. Did you have a question?
I was gonna ask, say like you have a linked list and you have an iterator, can you do arithmetic on that iterator?
So if you have an iterator to a linked list, you can only like do arithmetic with it going from the very beginning to the very end. Like you can't do like random access operations to it because the linked list nodes are not contiguous in memory.
Wait, so if you have a linked list of say like these 10 nodes, and then you have a point at the beginning, can you like add 5 to that iterator?
No, so a linked list iterator is only going to be forward if it's a singly linked list, or bidirectional if it's a doubly linked list. You can't do arbitrary arithmetic on it.
So you can only plus plus or minus minus.
Right, that's the only ones. Yep.
Okay, I'll let, okay.
All right, so back to me for sorting. I'm going to switch microphones here. Okay. Can everyone hear me? All right. So we got this section, and then we're going to go through heaps as well. So 2 more sections, and then we'll open it up for more questions and stuff. So sorting algorithms. We're going to go over the elementary sort algorithms, and then more of the advanced sorting algorithms. So starting off with bubble sort. Bubble sort is an algorithm where the largest element bubbles up to the top by swapping adjacent elements every time. So rather than go through the pseudocode, I'm actually just going to go through the animation from the lab slides. So if we start out with this list, we're just going to compare adjacent elements and swap them if they're out of order. And we're going to do this with n iterations over it. So we're going to get n squared time overall. But we'll see how it works here. So 38 and 53 are out of order, so we just swap them and we move to the next pair. This is in the same order, so we don't swap them. Here they're out of order, so we swap them. Out of order, swap, 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 swap. So now we see 76 was the largest element, and it bubbled up all the way to the end of the list. So at this point, after 1 iteration, we have fixed 1 largest element at the end of the list. Now we repeat this n times over each sublist, and we continue doing this. So the next iteration, the largest element, 61, is going to bubble up right next to 76 here. And eventually, if we do that n times, we'll end up with a sorted list at the end. So in the non-adaptive case, which is where we always do n iterations, our best case is n squared because it takes this n swapping operation as we go over the entire list, and we do that n times. So we're getting n squared in the best, worst, and average case. Memory consumption is O of 1 extra, depending on how much we use to swap elements. And it does end up being stable because it only swaps elements that are out of order. So the first occurrence of each element, if they're equal, stays to the left, because we will not swap them if they're not out of order. Does that make sense? Okay. So that is non-adaptive bubble sort. One optimization we can make is to make this adaptive by adding a Boolean flag for have we swapped anything in this iteration. So if we do this and it ends up being sorted earlier than n iterations, we can stop early and break out of the list, or break out of the algorithm. This is great for nearly sorted or sorted lists. So this changes our best case to be O of n, because like in a sorted list, which is our best case, we would do 1 iteration, swap nothing, and then break out immediately. Any questions on bubble sort? Yeah. What was that? Why did it work? So if we did no swaps, that means everything is already in order relative to every other element, which is the condition for sorted. Yep. So once we've established that invariant, we can break out early, because we know it's for sure sorted. Yes? You could do it the other way, yeah. Then you just bubble the smallest element down. Yep. The canonical version that we'll probably reference on exams is the bubbling up the largest element, but you could do it that way. Yep. Yes?
On an exam, if we're asked about this, we specified we're talking about the adaptive or non-adaptive one?
Yes. But in the general case, assume non-adaptive, unless we say otherwise. You can always ask, though. Okay. In that case, we'll go to selection sort. So selection sort is similar, but different. So in this case, we're going to divide the list into a sorted and a not sorted section. Similar to what we did in bubble sort, right? We built up a sorted section at the end. In this case, we're going to do the same thing, except the way we get the largest or the smallest element into that sorted subsection is going to be different. So we're going to divide the input list into sorted and unsorted. We're going to find the smallest element in the unsorted section and exchange it with the leftmost unsorted element. And by doing that, we increase the size of the sorted section. So we'll see. This is what the pseudocode looks like, but we're going to go over an example here. So we start with the entire list as the unsorted subsection, and the sorted subsection is empty. We're going to iterate and find the minimum of all the unsorted in this traversal. So we update the minimum every time we see a smaller element. At this point, we've found the smallest element. We're going to swap it with the leftmost element in the unsorted sublist. And now we've increased the size of our sorted sublist on the left there to 1, and our unsorted sublist is the gray elements to the right. So 14 is now locked into place in the sorted sublist. So that's the minimum. It's never going to move after that. In the next, we'll iterate through again, find the minimum. We'll find 29 to be the minimum, and we'll swap it with 38. And now 38 is going to be part of our sorted sublist, so we just keep growing our sorted sublist up all the way across until we get to the end. And then at the end, once the sorted sublist is the full list, we have sorted the list. Any questions on selection sort? Okay. So in selection sort, our best case is n squared, average case is n squared, worst case is n squared. That's because we do this find the minimum operation n times. And the find the minimum operation takes n time. Memory consumption, we're only using O of 1 extra space. But this is not stable because remember we swap with the first element. So you'll see in this example there's actually 2 53s in this sequence. One of them is at the start and one of them is at the end. When we perform this swap operation, the one that was before the second 53 moves to after it. So this is not stable. At this point we have ruined the stability of the sort. See, this 53 used to be before this one, but now it's after. So we've not maintained stability. Okay. Insertion sort, the non-adaptive version, we're again going to divide into a sorted section and unsorted section, but the way we get there is going to change again. So rather than taking the minimum or swapping out of order adjacent elements, we're going to take whatever is next in the unsorted section and insert it into its correct position in the sorted section. So to go through the slides, we already have part of a sorted section over there, and we have the unsorted section to the right. We're going to find the next element in the unsorted section, which is 29. We're going to take it and we're going to move it to its correct position in the sorted section by swapping elements next to each other. So we're going to swap with the adjacent element until it's in the correct position in the sorted list. So now we're done, and we've put 29 in its correct position in the sorted sublist. Again, in the next iteration, we would take 61 and we would swap it with the adjacent element in the sorted section until it was in the right spot. So we would swap it with 76, and then it would stay here because it's greater than 53. So we would not keep swapping after that. We do this for n iterations. Again, this swapping operation takes n time in the worst case. At the end, we'll have a sorted section which is this long and just the last element, and swapping takes O of n time, and we'll do this n times, so we get n squared complexity overall. So best, average, worst are all n squared again. Memory consumption is O of 1 extra. Again, we didn't use any extra memory aside from moving elements around and swapping them. And we did maintain stability actually, because elements that came after in the list maintain that they are after in the sorted list, because we only swap adjacent elements if they're out of order in the sublist. Any questions about this one? Okay. So that's the non-adaptive version. We can potentially take advantage of an adaptive version as well. Instead of swapping, we can move elements over and insert into the correct position, just like that. So in this case, we actually get n complexity, because in this case, for the sorted list, the full sorted list, we won't move elements at all. Okay. So we'll just look at each element. We'll try to move it. It won't move at all. And then we will just put it right back where it was in the sorted sublist. So we do n iterations of that, doing constant work each time. So in this case, still stable, still worst case O of 1. This is actually one of the best in practice algorithms on small input sizes. It's great for nearly sorted arrays as well. Yes? It ends up being faster in practice. So the algorithmic complexity is the same, you'll note, between this and like bubble sort, the adaptive version. But in actual like implementations that run on hardware, this ends up being faster because we do work on less items each iteration. But still asymptotically the same. Okay, stability. So if we're given a list like the one above, we want to sort the above list with respect to the set of pairs such that the first element 3 is the same here, so that the list of the second elements is sorted. So basically, we already have something that is sorted by second element, and we want to sort it by first element such that equal elements maintain their sort. So in this example, then this ends up being stable because elements that come after, which are equal in the first element, stay after in the sort. So we had 1, 2, 3 in the second position up here, right? We had 1, 2, 3 over there. So 1, 2, 3 should also appear in the output, even though all of these first elements are equal. In the second case, this breaks because we have 3, 2, 1 in the second elements for these last 3. So this breaks the sort because it was already sorted by the second element up there. So we broke it when we put 1 and 2 next to each other here in the opposite order. So I think this example is kind of confusing, but you can think of it as like, let's say we line up people by height, and then we want to sort them by age, but keep them in relative order by height if they're the same age. All right, so if we have a non-stable sort, we will ruin our original sort when we do that. But if we have a stable sort, we will get people lined up by age and then in increasing order by height within each age. Yes?
So you said selection sort is not stable. Can you go over why it's unstable?
Yeah. So actually, I'll go back to the slides because there's a great example in the. So here's the problem for this list. Right, we have 2 equal elements, 53 and 53 at the start. So this is like 53 sub 1, and this is like 53 sub 2. So when we do this operation of swapping with the minimum, or swapping the minimum into the leftmost position, that 53 sub 1 ends up moving to be after the 53 sub 2, which means we ruined the original ordering.
It's only when they're the same.
Yes.
Okay.
Yep. Stability is only a concern if you have equal elements. Go back here. I'm going to skip that. So the last one we're going to talk about is quicksort. There are other sorting algorithms you're expected to know. Feel free to ask me about them. The last one we're going to go over in detail right now is quicksort. So in quicksort, we are going to pick a pivot, partition our elements such that everything left of the pivot is less and everything greater than the pivot is right. And we're going to recursively sort those partitioned halves. So again, going back to the example from the lab slides, we're going to start with 2 pointers pointing to the ends of the array. In this example, we're going to pick the last element as our pivot all the time. So we take L and we increment until we find an item greater than the pivot. And we take R and we decrement until we find an element less than the pivot. Once we find those two, we swap and we continue the process. So we'll see what this looks like. L is greater than 42, our pivot. So we're going to take L and hold it. We're going to move to the right. And we're going to decrement it until we find something that's less than the pivot. In this case, just the original element, 14. So these are out of order with respect to the partition. So we're going to swap them around so that they're in the correct order. So 14 ends up left of the pivot, and 53 is going to end up right of the pivot. Now we're going to repeat. So we move left until we find something that is greater than 42. So we stop at 76, and now we move over to right, and we move it until we find something less than 42. So here we stop at 29. This is the first element from the right that is less than the pivot. We're again going to swap them. So that 29 becomes to the left side of the pivot, and 76 goes onto the right side of the pivot. Now you'll note at this point, we as humans can see that we already have a valid partition. We have everything less than the pivot to the left of this line and right of the pivot to the right of this line. But the algorithm doesn't know that yet. It doesn't know that left and right are one away from each other. So we increment left again. Once they're equal, then we stop. So at this point, we know that left and right are pointing to something which is greater than the pivot. We know that because 76 was swapped into the right position. So 76 is greater than the pivot. So it's always valid to swap with the end and put 76 at the end because it's already on the right half. So we can move it in the right half wherever we want. And we can put 42 right in the middle. So now we've established a partition. So everything right of the pivot is greater than 42. Everything to the left is less. And now we recursively quicksort both halves of this. So our next pivots would be 76 and 29 on each half. And we would recursively sort and do this process over again. Any questions on this partitioning process? That's the hardest part of quicksort. Yes?
So let's say the pivot isn't the last element, it's like the second or third element. Then when you pivot through the sequence, does the left or right skip over?
Yeah, so it gets a little bit more complicated when you choose pivots like that. I will say there are ways to do it and leave it at that. Really what we'll ask you, you can expect like the first element or the last element when we're doing partitioning like this, just because it's familiar. But if we're asking about other pivot choices, we won't ask you about how to implement partition necessarily. Does that make sense? Okay. Yes?
If left and right instead like both have to like decrement increment to be like in the middle, if it was like an odd number, would it have to check if it was less than or equal to the pivot first before swapping it?
So because we know that in the last iteration when they're equal, we got there by moving left in this last case. But you're talking about the general case where the right one moves and then they're equal?
If it's an odd set, so they both have to move, they both have to end up on the same.
Yeah, so there's actually, it can only be the case that one of them was moving. I guess in that iteration, one of them could have moved. But in the case where they're equal, only one of them moved that last time, right? They're not going to both move in that last iteration. But to answer your question, you would want to check to make sure that that element was either greater than or less than the pivot and do the appropriate thing. Yeah. Yeah.
So are you guys going to ask about valid partitions?
We may ask you, like, is this a partition for element 42 or something?
So what exactly does that mean? Like,
All it means is that everything to the left of the pivot is strictly less, and everything right of the pivot is either greater than or equal to.
so it's kind of like if you go through this algorithm, will it at one point reach that sequence, and it follows that the left side is less than the pivot.
Yep. Yes, question?
Would the partitioning also maintain the order so physically like 2 42s?
There are ways to do in-place partitioning where you do maintain the order. This algorithm doesn't do that. Yes?
How do you decide which order to, like which side? Because in the example that we had, you moved the left.
Yeah, so we always preferred left in this case. You could prefer right. It's this, yeah, it would work too. Yep. The thing is we just have to do them in some order. It doesn't really matter which order we do them in. Yep. Yes? Yes, so quicksort is recursive. And it will recurse on both halves after it does this partition step. Okay, so going over the complexity of quicksort, what happens if we select a pivot that always divides the list exactly in half? So this is the ideal case for quicksort, where we select the median every time. And then we'll get exactly division in half every time. So we limit our recursion depth to log n, and we do this linear partition step at every step. So we do log n times n partition for log n depth work overall. So that's how we arrive at our n log n complexity. Note, this is the best case and average case, but in the worst case, depending on our partition step, if we're not selecting the median element or something close enough to the median, we get an n squared complexity in the worst case. So you'll see in this case, if we select the largest element or the smallest element at every step, we end up with this partition n times, which takes O of n squared time. So basically, we're only eliminating one element every time when we go down and recurse. So we kind of build up these pivots on the right side, and the left side, we just recursively step down by one every time. So we get a recursion depth of n in this case, which is what causes this complexity. Any questions? So quicksort, best case, n log n, worst case, n squared, average case, n log n. The worst case, that's only for if you don't pick the median. If the median is selected, then you get n log n complexity. Memory consumption, we have log n for stack space because we're recursive. We do, on average, log n recursive calls. And it is not stable because of that partition step. The partition we showed you was not stable. So if we can find the median in O of n time, how does the complexity change? So I mentioned if you can find the median and partition it around the median, then you can do this in n log n time. So even if it takes O of n time to find the median, we can still partition in O of n time and find the median in O of n time for an O of n work at every level. So we're still doing log n depth if we select the median. So we get n log n guaranteed complexity if we do this. So what if this is a magical parallel universe where we can find the median in O of 1 time? How does the complexity of quicksort change? Again, hopefully if we can find it in n time and do it in n log n, we can also do this same step in n log n time, even if we can find it in O of 1 time. You'll note it's not anything less than n log n because we're still doing log n recursion and we're still doing a partition step, which is linear at every depth. So we're still doing linear times our depth, which is n log n complexity. Yes? So you recursively consider each half as its own array, right? So you kind of forget about the entire rest of the array. Yep. Okay, any more questions on sorting? Otherwise, I will hand it over to Omar for our last section on priority queues and heaps. All right, I will be walking around to answer questions as well.
All right, hello everyone. Take a second to stand up. We don't want anyone to have a blood clot. It's been a few hours. Okay. Test.
Yeah, I like the sum of the first one. Like,
Some people are out using the bathroom, so I'll wait a little bit until we see people coming back. All right, just half a minute and we'll begin.
Of course. Yeah. Yes. Yeah, so once we're recursing this half, we have to pick a new pivot. So every time we recurse, like this was our original array, we pivoted partition right? So at this point, we consider this half on its own, and then we consider this other half on its own. We pick a new pivot. So, not necessarily. So the left and right always are at the ends of the array. But in this case, it gets kind of weird because we're not taking the ends.
All right, let's come back and start talking about priority queues and heaps. Can you hear me well? All right. So let's start out with priority queues and heaps. By the way, the heaps that we're used to hearing about, like C++ memory storage with stacks and heaps, those heaps have nothing to do with the heaps we're talking about. Like the name is not related. Really an accurate way to describe the heap where you store this dynamic memory is a big pool of memory. So let's not think that heaps that store memory are stored in the same way that they are when we talk about them here. All right. So just quick redefinition of priority queues. It's an abstract container type that supports two operations. We can insert a new item and then remove the largest key. We've seen our implementation of priority queues of the sorted PQ, a binary PQ, and a pairing priority queue in part B of the project. Yeah, we're really just talking about the abstract container type. Here are the interface functions for an STL priority queue and the complexities we can expect. As you can see, push and pop both have to do with fixing, and so that ends up being related to the actual number of nodes that we're going to modify in the underlying data type, which is why we get a log n complexity for push and pop. Top is just reading a value at the top, right? We return a reference. I would look at the actual function signatures for all of the functions that you're going to use on the exam, because a lot of common mistakes end up being like just using an iterator as if it's something else, like an actual value, or not knowing that a function returns a reference or that it's a const, for example. So take a look at the function signatures. Yeah. Okay. So here's an example of how we might use a priority queue. Over here we see a definition for a functor. Remember, a functor is a class where we define or overload our operator that takes in two types and returns a Boolean. In this case, we have a comparator that takes in two requests and it prioritizes things that are more urgent. So if one of them is urgent, then it'll return true. I guess it's difficult to think about whether you should return true or false sometimes, because you're like, well, is the left thing the thing that goes on top of the right thing if it's below and the priority is higher? I think the best way to think about whether you should return true or false is to go back to thinking about less. We have the less functor. That's the standard functor that's passed in, the standard comparator that's passed into our priority queue in the STL, and it's going with an integer at least, and it's going to compare whether the left-hand side is less than the right-hand side. And if it's true, it returns true, where the right-hand side ends up being a higher priority and being on top of the left-hand side value. So always think back to what less does when you want to ground yourself and think, all right, what return value, what Boolean value do I want to return given these conditions? And over here we see the definition for a priority queue. A lot of mistakes that I've seen end up not passing in this middle parameter for the underlying data type. So over here we see a vector as the second template type for a priority queue. If you want to pass in a comparator, comp y, you're going to have to also say that it's a vector of type and then the first template parameter. So if we had a priority queue of integers and we want it to be a min priority queue, what would the parameters be? An integer PQ that is a min PQ. You'd pass an int, vector of ints, and the max functor. All right. So here's a sample question from a written exam. Suppose you're given an array of int size n and a number k. Return the k largest elements. Output does not need to be sorted. You can assume that k is less than n. So I guess just looking at this complexity limit right here, n log n, this might remind us of an implementation that might come as a more like obvious solution, right? You might just put things in a priority queue and then pop them out. What could n log n really mean? Like if you think about the simplest approach, we know that a priority queue popping takes log n time, and we know that if we're going to put in n items, every time we put in a value, right, those are n values, and every time we push, that's log n time. That might give us n log n. So maybe that's what it's hinting as the bad implementation. So we want to get a better time complexity than this, and we have O of n auxiliary space. So should I ask if people have a suggestion for a solution? Any ideas for how to implement this? Yep.
Next, we keep popping and pushing the elements. And then we look at the last element.
So you have a vector of size k, and then you heapify. Okay. So we know heapify, and we'll take a look at heapify in a second. That's O of n, where n is the size of the number of things that you're heapifying. So that'd be O of k in that case. And then you would be pushing values and popping them one by one. Okay. And then how many things would that be that you are pushing and popping? It's n minus k items. And so you end up with n times log of k, I think. And so that would technically be faster. Yeah, okay.
I think that's basically the intended solution. Yeah.
Yeah, well this one, yeah. So this one will heapify on the entire thing. Remember that heapify just means giving it a range for some data type. It doesn't have to be a vector. You could give it any iterator range, and then it's going to use these two iterators to figure out, all right, what are we turning into a heap? It turns it into a heap, and then we just pop the top k values. And each pop is log of n time, right? In this case, because the size is n. So log of n times how many times do we push or do we pop? That's k times, so k log n would be our complexity here. Any questions on this snippet of code? I don't want anyone to feel confused. Yeah? Yeah, so the question was, is it faster to construct the priority queue this way? Yes. Well, it really depends on how many items you're putting in, but if you've determined that you're going to put in 30 items into a priority queue, if you push them in one by one, what's the runtime going to be? Every push by itself is log n, and then we multiply that push by the number of things we're putting in. So that would be n times log n. Over here with heapify, as we'll see with the implementation, it's O of n. So we save a lot of time there. All right. So let's talk about properties for a binary heap. A binary heap is implemented as a binary tree with these rules. Each node has an equal or higher priority to the value of both its children. So the parents are, I guess, superior in priority. Again, there's a difference between priority and value, right? We might have a min heap where we have things with a higher priority be values that are lower. And here are the functors that we would use for max heap and min heap that we pass in as the third template parameter for each type. The implementation for a binary heap, a useful representation for a binary heap, and this is how essentially it's stored in the STL, is just as a vector, right? So when we pass in that second template parameter, we're telling it that we want it to store the actual values in a vector, and we want it to shuffle everything around whenever we pop, push, whatever within that vector. So we can represent it as a tree, right? The binary tree kind of represents this structure where the parent has values below it that have lower priority, but it's actually stored as an array. And there are a lot of convenient benefits that we get from storing it as an array. And so we can do random access into it, right? If we want to get the last element or the middle element for some reason, or for many reasons we would do that, it would take O of 1 time, right? We don't have to actually traverse, right? If I wanted to find this element, or let's say the middle element in a binary tree, you'd have to traverse and go around log n things, right? So finding a value or just searching for a value with a certain index is much faster when you have it stored as an array. And these are the indexing rules. Note that this is not for one indexing. So we might have seen an example. Some people might have implemented it this way in the project where you store things such that you have some empty value in the beginning, and then you actually start the entries in the heap. And this indexing is for the case where we have the value starting at index 0. Any questions so far? All right. And so as we modify our heap, we have to make sure that it's following the rules that we set for it earlier on, right? Which is that the parent must have a priority that is greater than or equal to its children. And we also want to always push or modify the container such that whenever we've decided that we're done changing it, once we've finished the call to push or pop, that it's always complete. So what does complete mean? It means that we've filled every level except for the last level, and that it's filled from left to right. So would this be a complete tree? No. The next node that would come in would have to go right here. So if we want to delete an entry from here, was there a question? Yeah. Oh, you're asking. Oh, cool. Okay. Yeah, and if you have any questions as well, feel free to interrupt me. But yeah, Austin's going around for questions that maybe you don't think might be specific. Okay. So whenever the priority of an item increases, that means that it should probably be higher up, or it might be higher up in the priority queue. So let's say this is the parent and it has a, let's say this is a max PQ, and has a root, a top value with 100, and this is 10. If you raise this to 900, it should move up, right? And so the logical step that we should take is that this should swap with the parent. So with a fix-up, we're able to solve the problem of what we do when a priority of an item increases. Once we reach the root, we know that there's no more fixing up to do. Or once we reach a parent with a larger or equal key. So we're kind of bubbling it up, right? That's how I like to think about it. Fixing up is kind of like bubbling up the values to the highest point they can reach. And the complexity is based on the actual depth of the tree, right? So the worst case scenario you can imagine would be starting at the bottom of the tree and fixing up all the way to the top. And log n, because we split, whenever we have a binary tree, we're splitting in half and half and half again. And so that actual spread of nodes ends up being log n in depth. Any questions so far? So that was fix up. But what about inserting? What about inserting a new entry? So if we insert a new entry, we need to make sure that we're keeping it with having the same structure, right? So we put in a new value here, but it might actually have a value that should be more highly prioritized. So let's say we put in 1,000 over here. We're gonna have to have this value bubble up to the top. And so whenever we push, we put it at the bottom of the heap or at the end of our array. So we put in this 1,000 here at the end of the array. We might have to resize this vector if this vector can't hold enough entries. And then we're going to do a fix-up on that node. What if the priority of an item decreases, right? So that means that its children might become higher priority than itself. So if I change this priority to 0, easy way to mess up. If I notice the 10 here, I'm going to go through an algorithm. I'm 0. My priority went down. I look to my left. The priority is greater. I swap. Did I make a big leap in an assumption or anything? Did I do something wrong? Okay, what was my mistake? Someone new. Sure. Sorry, what did you say? Oh yeah, find the greater child, right. So you cannot just swap with just one that happens to be a greater priority. Because what if this node is 100 and this node was 10, right? We have to switch so that the one that ends up taking its place is the rightful king of that subtree, right? And so we check both children, and then the one that is greater, if there is one that is greater, ends up swapping with that entry. And we keep going down until we reach the bottom, or until we reach something where the priority is greater than its children. So we see how if the priority of something decreases, we will call fix down on it. And again, we have a log n runtime, right? We're splitting in half and half the number of nodes that we can traverse. That's where we get the logarithmic depth. Any questions so far? All right. All right, so heap removal. If we remove an entry from our heap, we end up with a problem, right? There's a gap. And one logical way to fix this problem might be to say, all right, I'm gonna decide which of the children should take its position. Maybe I'll move the 36 up. And then you have to decide how to fix this, and then that ends up in being incorrect, I think. I think the simplest method, and the method that we're going to use, is to take the lowest value, or the last value, which might not be the lowest. It's just one that will necessarily help fix down the entries without leaving a gap, and fix down on it. So if we have, let me put some values here. This might not be easy to see from far away. So I'll just describe it. If we have a 100 on the top, let's say a 50 here, a 55 here, and a 0 right here, I pop from the top. And we want to have something trickle down so that the values that have the highest priorities fill in the gap. So we're going to take this 0 off from the bottom, put it at the top, and then we're going to call fix down, and then everything will end up being correct. Now here's an assumption that comes with fix down that's important to the intuition of what it means to fix down. Fix down is built on the assumption that the two subtrees on the left and the right are valid subtrees. You cannot call fix down on two invalid subtrees, which is why we do a bottom-up fix down, which we'll see later. So I know that this tree on the left and this tree on the right are both valid, so I'm able to do a fix down. It's going to find that the 55 on the left is greater priority, and it swaps, and it continues down to the bottom. So that was heap removal. So here's the 1 taking the place of the 100. And then we do a fix down, it swaps down to the bottom again. And that was log n. So here's a question for us. Assume you have the min heap going from 1 to 8. The heap property should be restored after every operation using the algorithms discussed in lecture. Perform the following operations. Delete the minimum element. Update the element 3 to have value 9. Insert a new element with a value 4. So in this case, when it talks about minimum, it's talking about value, not minimum priority, which is why none of these options have a 1 in them. So take a minute or two to work on this problem. Alright, so let's go through the steps right now. I'm going to pull out the iPad just so we can go through these steps. I think it's helpful to visualize and to compare how different people try to approach the same problem.
So I'm taking 465. Yes.
One moment, trying to connect the iPad. If it doesn't work, I will just switch back to the computer. It's trying to connect. Oh, rip. All right, there we go. All right, so here's our container. Let's start by building our binary heap. So we're going to have, let's use new color, green. So we'll have 1, 2, 3, 4, 5, 6, 7, and 8. There's a complete heap. We filled it from top to bottom, left to right. We're going to start by deleting the minimum. So that means this value. When we pop from the top, what are we going to do? We're going to take the last value, swap it with the top, and then we're going to do a fix down. So I'm going to remove this 1, replace it with the 8. All right, and then I'm going to do a fix down. Note that this is a min heap. So it's going to look at either the 2 or the 3. Right, the lowest, the higher priority value is the lower value. So we're going to move the 8 down. Unfortunately, you can't copy paste text like this on the exam, so it's hard to scribble down like changes to the tree. What I like to do is every now and then, let's say there are multiple steps for your for what you're doing with the heap. I like to do this step and then copy over the priority queue so that if I made a mistake in the second step, I don't have to redo all my work. The worst feeling is frantically going back and redoing all the work even though you know that the first step might have been done correctly. So that might be a good strategy for you. So we're going to continue. We're going to move the 8, swap it with the 4. Okay, so here's our intermediate heap. All right, step 2, we're going to update element 3 to have a value 9. So now that this 3 is going to become a 9, that means that we're raising its value or lowering its priority. That's a 9. Okay. And so we're going to call fix down on something that has a lower priority. So the lower value is the higher priority. The 6 takes the place of the 9. So we're done with that. And we're going to insert a new element with value 4. So inserting new elements. Here's a new value 4. Right, we fill from top to bottom, left to right. And then what are we going to call on that 4? What fix? Fix up. So we're going to call fix up. It's going to check its parent. They're going to swap. 8 goes down here, 4 goes up. And then once we find that these two 4s have the same priority, we can stop. All right, so now we're going to actually write out our outputted heap in vector form, in array form. So we're going to start with the 2, 4, 6, 4. Oh, what was that? 6, 4, 5, 9, 7, 8. All right, and that should be our answer. Let's switch back to the laptop. Austin, unlock it. Sorry. Thanks. Yep. All right. Mirror displays. Oh. I think I might need to just replay the presentation.
1 second.
Oh, I see. Yeah, just do a 3 from here. Okay, thanks. All right, so. I think that was our answer. It was. Okay. All right, let's keep going. I don't want to go further than the allotted time. All right, so which of the following statements about heaps is false? There exists an algorithm that can turn any array into a heap in theta of n time, where n is the number of elements in the array. The array 1 through 11 represents a valid min heap. And then deletion of the most extreme element from a heap can be done in theta of log n time, where n is the number of elements in the heap. So the most extreme element, this deletion, we already talked about this bottom case, right? That's just popping. And popping is log of n, so that's not true. B, to check B, we'd have to actually check each of the values one by one. Now some people will actually draw out the tree, but I don't like to do that. I like to draw lines from each subtree's root node to its children. So I like to draw a line from the 1 to the 2 and a 5, and then I draw a line from every number that hasn't been connected to a number on its right yet to the next ones that haven't been connected at all. So I connect the 1 to the 2 and the 5. Okay, those are both lower priority. And then the 2 to the 6 and the 4. And then the 5 to the 3 and the 9. And then we see our problem right here, where we went from 5 to 3, where a lower value or higher priority element is below the 5. And so we know that this is not a min heap. So our answer over here is B. Okay, any questions so far? Yep. For A, oh yeah. So there exists an algorithm that can turn any array into a heap in theta of n time. So that's heapify, right? Heapify takes our vector, we can pass it an iterator range, and then it's going to do a heapify in our bottom up fixed down. So that's actually a segue into the next slide. So what is heapify? We call it on an unsorted vector, and it gives us a better runtime than if we just inserted every entry one entry at a time. And it calls fixed down from bottom up. That's the more efficient approach. And it saves time on the last n over 2 nodes. The bottommost level is what it's talking about compared to top-down fix up. Yeah, and this is what's called when you call the range-based constructor on a heap. So fix up, less efficient. I guess the real takeaway from this slide is that the greatest amount of work is happening on the largest set of nodes. So n over 2 on this end, this is saying the depth that we're looking at. So depth of 0 is like the root node. At the bottom of this table is log n, so we're all the way at the bottom, right? The number of nodes that exist near the bottom is closer towards n over 2, right? So if you have 1 and then 2 entries, and then you have 4 entries, you see how that doubles. So for half of all the entries, we could do log n work. Compare that to a bottom-up fixed down. With a bottom-up fixed down, we do almost 0 work for the majority or half of the elements, right? For the bottom half, we do close to 0 work, because if we call it fixed down on this node, there's no work to be done. Call it fixed down on this node, no work to be done, right? So we save a lot of time by doing that and making the most work happen in the sparsest or the smallest groups of nodes, which are closer to the top. And so we end up with a better runtime. And this runs in O of n. Yep. Any questions on these two approaches? Yeah? If you wanted to call the heapify algorithm, would you just create a priority queue? Yes, and you would use this approach. So if you were told to create a heap out of a vector using heapify, you would just do bottom-up fixed down. I would draw a tree like this, and then call fixed down on each entry. Any questions? Other questions? Yeah. Oh, so are you talking about doing it by hand or doing it with code? With code, it does it by itself, right? There's never a priority queue that is not fixed. It's always your priority queue is always in the correct state, right? That's the whole idea of having invariants for C++ classes. So you're guaranteed to have it be like, following the invariant where every parent has a greater priority than its children. All right, any other questions or follow-ups? All right, let's keep going. Oh, yeah, another one. Sorry, I couldn't hear you. Yeah, so the question was, does the bottom half of the heap need to be sorted? We talked about sorted and ordered data types in the last lab, and we came to the conclusion that heaps are not sorted. The actual values that are represented in an array don't come in a sorted order, right, in a sorted form. Over here we see 13, then 3, then 5, right? To follow the rule that your parent has to be greater than you in priority does not guarantee that within one level there's a sorted property. Oh, I misinterpreted it. You meant the order? You're saying the order in which we do fix down on the bottom. Yeah. Yeah, so the question was, if you call fix down, do you have to call fix down on the bottom row or the bottom? Yeah, no, you don't. You could implement your code so that it skips those entries. Now that might be more complicated. It might be easier to just call it and let it do its thing, and it'll just say, oh, there's nothing under me. I'm not going to fix down. And because it doesn't actually do any fixing down, that's fine. So if you call it, it's still not going to do much work. You're just wasting time with a function call, I guess. Well, that's not really a big deal. But yeah. Any other questions? All right. So assume you have an unsorted vector with the following contents. Suppose you were to turn this data into a heap by doing repeated fix down operations starting from the bottom, as we demonstrated. With the goal of creating a max heap, what would the vector contents look like after being heapified? The time is 3:47. I don't think I should go through each of the steps, but we've seen fix downs. Right? The idea is that we go from node to node, from right to left, bottom to top, calling fix down. And at the end, as long as we're following this rule that we want it to be a max heap, we'll end up with the correct answer, which is A. All right, if you want to take a photo of that. I mean, the slides are online, so you don't need to. All right. So priority queue implementations, the binary, a binary heap. A binary heap can be stored conveniently. What is this slide? Oh, right. This is showing why this indexing works. So we're given these expressions. Might be useful to put on your cheat sheet. Assuming that the root is at 0, right? How do you get to your child? You multiply by 2 and then add 1 to get to your left child. So we multiply 3 by 2, we get 6, then we add 1, and there we are at the child. So this is just a helpful way to visualize the indexing and its correspondence with the underlying vector. All right. So we're looking at a call to make heap. We're going to do a fix down from the bottom up. And these nodes don't have any work to be done. And you start on the 3, nothing to fix, nothing to fix. 4 swaps of the 7, and then 7, and then the 4 tries to swap again, nothing to do. 5, we swap with the 8, which is a higher priority. The 5 swaps to the 6 until it reaches that settled value. And then we call it on the last node, which is the root node. 2 is less than 8, and it's less than 7, but 8 has a greater priority. Swaps with the 8, and swaps with the 6. And then the greatest of the 2 children is now a 5. And so there we called make heap or heapify. They're the same thing, make heap or heapify, on this unsorted data type, on this unsorted array. All right, and that's the output heapify. To insert a new element into the PQ, we push it to the end of the vector. then we call fix up. Here's our 6 going up until it reaches something with a higher priority or a greater or an equal priority. Any questions on what we just saw? Okay. Popping. So we're going to swap with the last element, and we call it the last element because it's the last thing at the end of a vector, right? Your vector might have more space reserved, but when we call vector dot, like v dot back, you'd be getting that last value. So if you want to keep the value actually stored at the end of the vector for a heap sort, you wouldn't actually pop it off of the vector. So we swap, and then we call fix down, assuming a smaller size for our heap. Any questions on that process? All right, I'm trying to get through the slides. All right. All right, so there we go. We have log n on push and pop related to the depth of the tree. And heap sort. So we're taking advantage of heapify, of the way that the heap structure is has the highest value on top, and how we have that invariant relationship between the parent and its children. And we can take advantage of it to actually sort the underlying vector. And the worst case runtime is n log n. It's not stable. So the first step for heap sort, if it's already a heap, we can just move on to the second step where we actually do our sorting function. But if it's not sorted, and let's say we want to write our own heap sort that works on a vector, all it's doing is taking a vector, doing a heap sort on it, and then it outputs the resulting vector that's sorted. Sorted just as if you called bubble sort on it. And so we're going to, let's look at an example. We're going to pick the highest value. I guess a good way to describe this as is that our heap always has the next step in our sorted vector at the top. Right? We know that our vector is going to have the highest value right here, right at the very end. And so we take the highest priority value from the top and we put it here. So for a min heap, the 0 would go here. And then we lock this position, this growing end of the vector, the sorted end of the vector. And then we fix our heap again, and now we have a new top. And that new top has the next greatest value, right? If we keep popping from heap, right, we're going to get items in descending order. So because of that ordering, because of that sorted ordering that we get, the next item we put in, we put it at the end, and then we have a new, I guess, barrier representation where the size of the heap goes from this vector beginning all the way to right before the last entry that we locked in place. And if we repeat that, we end up with a sorted vector. So we're going to move the 8 to the last position. Now it's locked. This bar represents what we consider to be the size of our heap. But we're not actually popping from the vector. And then we do a fix down on that root. And then we repeat the process. Purple means that it's been locked in place. 7, we're going to swap it with the last element in what we're imagining to be a sub heap, or when we exclude the 8. Swap, fix down. 6 with the 3, and so on. Oh, what was that slide? So preparing for the exam, know how to represent a heap as a vector, know heapify and heap sort and how they work, and the complexity, and do some practice problems. I think the most valuable thing for you to do is just get used to it. Even though you might understand how it works, just having a good technique for how you write it out and solve it on paper is important. All right, so that's heap sort. And I think we are done. All right, so thanks for coming, everyone. We'll be here for a bit to take more questions. But other than that, good luck on the exam. Thanks for coming. Hi.
Are you going back to Central, Daniel? Going back home. I'm gonna work on my 217.
How are you feeling here? How are you feeling here? How are you feeling in this cycle? If this cycle, I know what I was in this room.
I use the previous presentation.
Pay attention. Let's pay attention. So, if you see something else, if you want to keep comparing points, you need to
So these curves don't have to actually look through
So you have to get because of the actual I would say but there's a you say that whoever points to you as a sibling, it's a point to your sibling. But there's a case in which whoever points to you don't exist because you're the first greatest strong. I've been talking about that case for a long time.
No,
But that's
no, I would agree. Yeah, for deep store, because deep store is last step.
Deepify is part of it.
Yeah, Deepify is in like the binary.
So like it's like you're given an array.